Okay, hi everyone. This is the screencast that I was referring to. That was part of homework for tonight. What I'd like you to do is to make sure you listen to this screencast and do the homework before you go to the review problem set, okay? Because the review problem set will have content that you need from this screencast. So I'm going to pull up this handout from class today, and I'm actually sitting out in the beautiful afternoon, fresh air and kind of sunny afternoon watching football and cross country run laps. There goes Nancy. Hi, Nancy. Okay, so from class today, we did this, number 1 and 2. I'm going to talk about these 3 boxed expressions for a second, okay? In class, we said that this expression right here correctly is one of 2 things. You can call it the average rate of change of position over the interval of time from t equals 2 to 9, or you can recognize that average rate of change of position is no other than just velocity. So saying average velocity or average rate of change of position over time t equals 9 in inches per second, they are saying the exact same thing. I am going to, however, focus on this expression, this version right now. In other words, this one, where I use average velocity, because I want you to see something here. Notice that if I write this as average velocity over t equals 2 to 9 in inches per second, I'm making note that it is the average it's the average velocity over time, t equals 2 to 9, and the integrand here happens to just be velocity, okay? What I'm doing here is working my way towards a shortcut I'm going to show you. Let's go down to the cats one. This one was interesting, okay? I think what we said today in class for this one, we said that this expression describes the average rate of change in number of cats over the interval of time from t equals 2 to 9. In fact, I believe we literally just said this. We call this the average rate of change in number of cats over the interval of time from 2 to 9, and the units are cats per hour. I'm going to replace the phrase rate of change in number of cats to just call it speed of cats. And I probably should just put some like quotes around this, okay? So in other words, what I'm doing is I'm just taking the rate of change phrase out, and I'm asking myself, when I say rate of change in number of cats, what other entity describes the rate of change in number of cats? Well, it's the speed of cats, okay? So it's just in quotes. And I'm going to notice something here. This integrand, c prime of t, if c of t was the number of cats function, as I say above here, then c prime of t, guess what this function is? This is the, speed of cats function. Okay, so what it looks like here is it looks like a similarity. If I am looking at the definite integral from 2 to 9 of some function dt, and if I divide it by the interval of integration, right, this expression, which is no different than this expression, seems to equal an average, whatever the integrand is, average velocity, average speed of cats, over that very interval of integration, okay? Let's check the last one. This last one was a pretty funny exercise. So if c of t, and I'm going to kind of quote Oliver here, c of t is number of cats, right? That means the units of c prime of t would be number of cats per hour. And then c double prime of t would be number of cats per hour squared, okay? And so, as you see, if we go in this direction, right, if we head in this direction, we keep kind of, our units change as such, right? We go cats per hour, hour, which is cats per hour squared. And so Jason was asking me, well, does that mean the units for the antiderivative of c of t would be not cats, because cats is at c of t, but this would be like number of cat hours? And the answer is yes. Now, all of us are going to say, what in the world does a cat hour mean? And a cat hour means absolutely nothing that's useful. But in terms of just using units, you see what's happening. Because if I start at cat hours and I take one derivative this way, I get cat hours per hour, which becomes just cats, right? If I go from here to here. And then I have cats per hour, I'm here, and so on and so forth. So the units of this function is cat hours. But what's interesting here is, let's take a look. Okay. So here, right, because C of t is the cat function, the numerator's units is going to be cat hours. Okay? But the denominator's units are hours, because 2 to 9 are hours. So we have cat hours over cats. So this is the average number of cats, right? And it's the average number of cats. And you'll notice the integrand here is the number of cats function. So it seems to be, if I look at these three examples all together, it looks like in all three cases, if I have this expression, hi girls, say hi to my BC Calculus class. This is Sarah and Lauren Peterson. Hang on, please. If I look at these three examples, there seems to be a commonality. That if I have a definite integral, let's be very careful, if I have a definite integral and I am dividing it by the interval of integration, the value I get here is the average, whatever the integrand is. If the integrand was a speed of cats function, I get an average speed of cats. If the integrand is a cats function, I get average number of cats. If the integrand is a velocity function, I get the average velocity. Notice what I'm doing here. Basically, if I make myself take the rate of change wording out of each descriptor, what I find is a match between the integrand and this entity here, that which I'm finding the average value of. Do you understand? Once again, if I take away the rate of change phrase, the verbal descriptor here ends up being the average value of whatever the integrand is. If the integrand is a speed of cats function, this is the average, whatever that entity is, speed of cats. Go ahead and let's do number 3 together, okay? And actually, hold on, don't look at number 3. Do number 3, then replay me, okay? If you did number 3, what I'm going to look here, you can go ahead and check these. You can check A, C, and D fairly quickly. D is a little tricky. This is the average rate of change of acceleration over 2 to 9. Units are meters per second cubed, okay? There is a word for rate of change of acceleration. It's called torque. Is it called torque? Or is it called hyper? I don't remember. But it's the average rate of change of acceleration. Let's look over here now again at this one. Okay, right here. Let's see what happens. Well, this is, maybe you wrote average, maybe down here you wrote average rate of change of velocity, right? Over the interval of time from 2 to 9. Units are meters per second squared. But don't forget, rate of change of velocity is none other than just average acceleration. And once again, what I'm seeing is the average, the thing which I'm finding the average value of is matching the integrand. All this is going towards the following, which is something called the Nick Sawicki. Say hi to my BC Calculus class.
Hi, BC Calc.
It's Nick! Okay, this leads us to this theorem, and believe it or not, this is not even a theorem. This is a conclusion, right? And it's so kind of anticlimactic. This is called the average value of a function theorem, or is that a theorem or is it a lemma? I always confuse the two. Anyway, the average value of a function. Now, this is what we've just been talking about. Okay. This is so incredibly straightforward in isolation, okay? What's really important that you know, though, is that when you work through a problem set, like you're going to on the review problem set, you will see questions where they will ask you something like, what is the average speed of the frogs in this race? And maybe you have a speed function, right? if you know this, you can just input in speed function here over the interval of time that you want the average speed divided by b minus a, okay? But you have to just be mindful of units always, and where this can be very trickily incorrectly used. So, for example, if you go to your review problem set with me, okay, sorry, I referenced the wrong thing. If you go to your textbook, and all I'm looking at here is page 389, and you don't necessarily have to turn there because you're looking right there with me. If you look at this statement right here, right, number 24, just look at 24, okay, because you can't see my pointer. I'm on a website here. But number 24 is saying, suppose that the acceleration function of a particle moving along a coordinate line is here. You're given the acceleration function. Find the average acceleration of the particle over the time interval 0 to 5. They really even shouldn't have said by integrating, because they should make you think about it. Find the average acceleration of the particle over the time interval from 0 to 5. So here, you want to know what is the single most popular wrong answer? The single most popular wrong answer is to do this. Is to say, okay, I'm going to say the average acceleration is going to be a of 0 plus a of 5 divided by 2. This here is not the average acceleration over the time interval 0 to 5. This is an average of two accelerations. One acceleration at time 0 and one acceleration at time 5. Okay? The average acceleration over the interval from 0 to 5 would be the definite integral from 0 to 5 of a of t dt, all divided by 5 minus 0. And you want to compute this and have the correct units. The units here would, of course, be the same as the units for the integrand. This is the single most popular incorrect thing to do. Let's go to part B. Suppose the velocity function of a particle moving along a coordinate line is v of t. Okay, so B is a different question. Find the average acceleration of the particle over the time interval 0 to pi over 4 algebraically. Now, notice here, it's asking you for the average acceleration. It's asking you for the average acceleration, right? But what they gave you here was the velocity function. So if you want average acceleration, you can do this now two ways. You know, average acceleration is the same thing as average rate of change of velocity. So you could make the statement that, well, v of 5 minus v of 0 over 5 minus 0 would equal the average rate of change of velocity from 0 to 5, or the average acceleration from 0 to 5. You could also say that this is the definite integral from 0 to 5 of that velocity function given to you, all divided by 5 minus 0. Okay? Where this becomes really, really convenient and nice is when you start using your calculator, okay? Because your calculator makes computations like this super, super easy, as opposed to, necessarily having to compute this if you have a pretty treacherous looking function you're inputting into. Okay? Which brings me to now your homework, which is going to be on page 389, number 15. Okay, I'll write it down here, page 389, number 15. And here it is. This is your homework, okay? So watch the screencast, do the homework, then the review problem set. All right. Have a good evening, and I'll see you for question day next week.